So let's talk here right now a little bit about chlorination. Chlorination, again, is probably the most common method of disinfecting drinking water in the United States and beyond, all around the world. And also, chlorination is probably the most common method used in the United States for disinfecting even swimming pools. Now, how does chlorination work? So you should know that chlorine is very reactive. A lot of chlorine gets used up or neutralized or bound to things that are non-living. And when that happens, we may increase our total chlorine, but if it gets bound up, then it's no longer free. It's no longer residual chlorine. So the microbes may be able to escape disinfection. If there's a whole lot of them, the chlorine gets used up, they may be able to escape disinfection. So to prevent that disinfection escape, breakpoint chlorination is sometimes used. Breakpoint chlorination is the name for this process that is used for evaluating or ensuring that a sufficient amount of chlorine is left to disinfect and maintain disinfection throughout a drinking water distribution system. We want to have some chlorine left in the water for the system. It keeps the pipes in better condition. In the event that there is a failure in the system, you're not going to worry about people getting sick because there's still some chlorine left to disinfect. So how does breakpoint chlorination work? So let's look at it. Here is chlorine residual on the y-axis, and down here on the x-axis is the chlorine added. You can think of this as total chlorine, and you can think of this as free chlorine plus chloramines. Chlorine residual has the ability to disinfect. So this is the killing power of your water. Total chlorine is just indicative of whether or not an effort of chlorine addition happened or not. So look, when we first start adding chlorine to a water sample, there is no residual chlorine if there's any reducing compounds. Now, if you were adding this to deionized water, obviously it would go up immediately. There's nothing for the chlorine to react with. As you add it, it's all available. But if you add chlorine when there is stuff in the water, and I call it stuff, I'm talking about some types of reducing compounds. We'll talk more about them. It could be natural organic matter. Stuff that we probably don't want in the water that we'd hope to get out of through sedimentation and filtration steps. But as we add chlorine, we'll see this formation of chlororganics and chloramines. And it hits a high point here. As we continue to add it, the chloramines start to get degraded, and it goes down, but you continue to have more and more chlorine added, and you'll eventually get to a break point to where no matter how much you add at this point, it's proportional. Every bit that's added also becomes residual once you get past the break point. And this is called breakpoint chlorination, finding out where that step is at. So let's go through these different steps really quickly. So step 1 in breakpoint chlorination, that's this one. Chlorine is added and it's immediately reduced by stuff like iron, manganese, hydrogen sulfide, natural organic matter, ammonia. There are all kinds of other things that will react with the chlorine and enable the chlorine to become essentially useless for disinfection. Notice, no free chlorine is left, no chlorine residual. So things like natural organic matter, which could be like soils have like humic acids in them and all kinds of stuff. Cyanobacteria release all kinds of little organic compounds in the water. All that stuff interacts with the chlorine and uses it up. So as we add more chlorine to satisfy that chlorine demand, especially if there's ammonia in the water, nitrogen compounds in the water, chloramines will start to form. And they'll form proportional to the amount of chlorine you're adding. And guess what? Chloramines can actually do disinfection. And if dosage stops here, your chloramines will be used up. Chloramines will also react with other organic matter in the water and they will get degraded. Chloramines are not as long standing in the water system as free chlorine after the break point. So this was step 2. Step 3, as we add even more chlorine, now this is the odd one, right? Step 3, we're adding more chlorine, yet our chlorine residual is falling, okay? So the chlororganics and the chloramines, they're destroyed. And then step 4 is after we've achieved that break point, it goes up and everything thereafter is free available residual, which includes free chlorine and chloramines. So upon adding more chlorine at step 4 beyond that break point, the chloramines and chlororganics, they're all destroyed. So now everything else that will be left here will not form chloramines but free chlorine. So here's another image here, okay? So let's look more into what is chloramine and then also what is free chlorine. Both these represent the chlorine residual and can do disinfection. So here's chloramine, and then what is free chlorine? Free chlorine, when it goes into the water, it produces hypochlorous acid and it can also produce hypochlorite ions. Hypochlorous acid, the acid, is the most potent disinfectant. However, the hypochlorite ion can also disinfect. So when we add chlorine to water, Cl plus H2O, we form this, which is hypochlorous acid, and we form the hypochlorite ions. Chlorine added to water is free chlorine when it forms hypochlorous acid and hypochlorite ions. And there are other types of chlorine agents that can be used. Now I'm going to go back to this really quick. I want you to remember from the previous videos, number 1, hypochlorous acid is formed more in water with a higher hydrogen ion concentration. So if the water's got a lower pH or it's more acidic, it's going to have more of this, which has actually got more disinfecting power. Now, does this OCl, the hypochlorite ion, does it also disinfect? Yes, it does too, but it's not as potent. So it's important to remember that from a coagulation and flocculation standpoint, early on, higher pH is better for the water plant. And then as you do disinfection, lower pH allows for adequate disinfection to happen more quickly. But when the pH is in the 7 to 7.5 range or 7 to 8 range, you know, you're not talking about huge differences here. So both are adequate. Together, the hypochlorous acid and the hypochlorite ions are free chlorine. So some of the other types of chlorine methods that are out there are using chlorine gas. And there's some health risks that are out there if you do that. There are different hypochlorite solutions. One, the most common one, is sodium hypochlorite or bleach. So what they use at the water plant comes in drums, and it's more like a 15% solution versus 5%, like household bleach. And then there's also calcium hypochlorite that can also be ordered in drums and be fed into the drinking water system as well. This is a little image from a study of a former student who was working on a project in another part of the world where they were trying to do their own disinfection using some unique faith-based organization's system. And although they may have been well-intentioned, when she did their survey of their samples, the chlorine levels were not in the ideal disinfection range for that community or for what the World Health Organization thought it should have been. And then day 9 or so, they notified them and some cleaning happened to the system, and then it may have resulted in just bleach being dumped in over multiple days. I don't know. And then you had a lot. But needless to say, knowing what the free chlorine levels are is important for knowing the disinfection capability of the water, how safe is the water to drink. And you can see on the days when the disinfectant was present, day 12 and 13, there were no total coliforms. But you saw a lot of total coliforms in that water. with respect to the E. coli levels, we saw very little E. coli levels when the disinfectant levels were there, but on the days when there was no disinfectant, the E. coli levels in their drinking water were unsafe, so much so that on several days it wouldn't have even met the drinking water standards for the United States. So it's a little bit about, to measure chlorine and learn a lot about how well it can disinfect even in developing parts or low-income regions of the world. So the other chlorination steps that are out there, I want to mention them again. One is, let's talk about this. These 15% solutions are very corrosive, so you have to be very careful when working around it in the water plant. But you really have to be careful at a water plant where they're using chlorine gas. And I would encourage you, if you're interested, to study Fritz Haber, the Jewish-German scientist who essentially created nitrogen fertilizer from atmospheric nitrogen, that most or half of the nitrogen in all living people on the planet probably comes from his method for fertilizer, and how important it was for him to develop that method to prevent people from fighting wars over bat guano for fertilizer nitrogen from South America that people in Europe were fighting over so people could get fed. So Fritz Haber got a big medal, maybe even a Nobel Prize or something for his work, but then he also learned to weaponize chlorine gas against the Allies on behalf of the Germans, and he also helped develop the chemical that was ultimately used on people even from his lab before he fled his country, that was used to kill Jews in the concentration camps in those gas chambers. So Fritz Haber is a very interesting person, but he learned that chlorine gas could be weaponized. It's very dangerous stuff. So it's interesting. I'll put a link up there about him. Now, when we do disinfection, like with any disinfectant, contact time matters a lot. So shorter contact times are needed with higher concentration. So chlorination works with contact time and the concentration. So the concentration, not just the total chlorine, but for disinfection, it's the concentration of the residuals that are there. And then we said pH. pH. Remember, lower pHs favor the hypochlorous acid, which is a stronger disinfectant than the hypochlorite ion, OCl. So there are other methods of disinfection that are out there. And I'm going to ask you, why are other methods out there? Why are they gaining attention? And the main reason was because in 1998, the EPA promulgated a disinfection byproduct rule that said that these disinfection byproducts that are known carcinogens, among other health effects, are caused through chlorine interacting with stuff in the water. So rather than using sodium hypochlorite, you could use chloramines and actually develop less disinfection byproducts, or use ozone or UV. Now here's a case study here, a little bit of information at least. And I want you to know that about 20% or more of Americans get their water now from just chloramines, and they do produce less disinfection byproducts. However, that one scientist you may have learned about from one of those videos, Dr. Edwards, Mark Edwards, he showed that chloramine was responsible for pipe corrosion in Washington, D.C. that resulted in elevated blood lead levels in people living in Washington, D.C. And the US EPA encouraged it, and then when their own scientists discovered problems, they tried to hide it, and Dr. Edwards exposed it. The agency has a strong track record, but there were certain folks within the agency that tremendously harmed the reputation of the agency, and Dr. Edwards was responsible for helping show that this switch from the sodium hypochlorite to chloramine in a well-intentioned effort to reduce DPBs resulted in elevated lead levels because free chlorine acted as a good anti-corrosion agent. Without free chlorine, we need to add an anti-corrosion agent. So we're going to watch a little video, or I'm going to put up a slideshow up on Flint, Michigan, and how they could have prevented a lot of their catastrophes with their water by adding a chemical like zinc orthophosphate. So ozone is another type of disinfectant that is out there that doesn't produce those disinfection byproducts like chlorine does, but it does produce some other disinfection byproducts that are ozone related. It does have the ability to disinfect as good as chlorine. It's been used for over 100 years. It's EPA approved. You don't need, to worry about trucking it in. You can generate it on site. And it can inactivate cryptosporidium or giardia or be used in tandem. Now, cryptosporidium and giardia, they die from chlorine, they'll die from ozone too. Now, why would somebody not want to consider using ozone? So ozone, with all of its good things, does require a lot of electricity to generate. It doesn't leave a residual in the system. So it's not like you've got free chlorine that stays out there. Ozone is quick to be made and it's quick to disappear. So it can only disinfect for a brief period of time, and then you'd have to add more. And the corrosion associated with ozone, especially at the water plant, can be pretty potent. So you have to replace a lot of things or have very strong anti-corrosion control methods. UV treatment, where they lower these UV lamps into the water system. UV works. It can, disinfect by the genetic material, the viruses or the things you're trying to disinfect, bacteria, parasites, whatever. The UV damages the DNA. UV lights on these low pressure lamps, there's kind of a whole bank of lamps that can be lowered in. And there's a lot of places around the world that are using them. But you have to have your water be very clear, no turbidity, for these things to be most effective. In UVC radiation, of all the types of ultraviolet radiation, this one, UVC around 264 to 263 nanometers of light, is the most effective for having killing power. And UV works by breaking the DNA. So the thing may survive a little bit longer, but it's not going to be able to replicate in the event that a host, ingests it or something like that. So we're going to go over the review here in the next video.